Some keyboard instruments are equipped with so-called ribbon controller. This allows you to conveniently control a selected parameter by touching and sliding your finger. It's a fun and practical way to create interesting sounds on electronic instruments. Unfortunately, my keyboard didn't have such a tool, so I decided to try making one myself. In this video, I'd like to show you an open source project for a small MIDI controller that you can assemble yourself. Using it, you can add new features to your synthesizer. With some extra effort, you can even enhance the control with techniques inspired by older analog instruments, but we'll discuss that in part 2 of this video. Let's first look at the basic version of this controller, which I named kmMidiMini. In its simplest form, it doesn't have a built-in MIDI port. Instead, there is a connector where you can attach a DIN plug for MIDI output via cable. USB is used only to power the device. It has 2 buttons to control operating modes, LEDs to indicate its status, and pins connecting for Sensing Linear Potentiometer that supports pressure sensing. You can attach this mimicked ribbon controller to your synthesizer's housing wherever it is convenient for you. The ribbon can be either soldered directly to the PCB or, in this case, connected via a socket that allows easy disconnection of parts. One option is to place the circuit board inside your device and let the connectors outside through the housing. For now, I've attached the controller on the side of my synthesizer and connected it with a cable. Plug the DIN cable into MIDI socket and USB into the power source. Turn on the synthesizer and the controller status LED starts blinking, indicating it's ready to work. Let's set up an instrument and see how it works. By default, the controller responds only to the position of your finger and sends parameter number 22, which is usually assigned to ribbon controllers. When you stop touching the ribbon, the controller value stays at the last sent position. Pressing button 1 will make the controller reset to neutral value when you lift your finger. Button 2 enables a mode where the controller sends an additional parameter to the synthesizer, responding to the pressure applied. In this case, it controls parameter 71, which adjusts the filter resonance. Alright, let's try using this device to simple arrangement. When creating this project, I aimed to design it in the way that apart from its main functionality, the hardware board could also serve as a small development kit for other projects, not necessarily related to musical instruments. Let's take a look at its connectors and capabilities. Starting at the top right and moving clockwise. Here we have a DIN-type MIDI output connector, which can be directly connected to a musical instrument using a standard MIDI cable. Next, there is a pin connector that can be used with dedicated MIDI cable, like this one. This connector also allows for power supply connections. Together with the other connectors, it can also be used to connect shields that expand the board's capabilities. Here you can see an example of such shield. It adds MIDI input and MIDI through connection to the output available in the basic version of the board. As you can see, it also utilizes the connector located on the opposite side of the PCB. The connector below exposes E2C signals, allowing for the future functionality extension, such as adding a display. In the center of the board, there are two buttons that enable you to switch the device's operating modes. More details about this can be found in the manual. At the bottom of the board, there is a USB connector that functions as a standard MIDI interface. The two previously mentioned buttons may not be sufficient, so I also added an infrared receiver at the very bottom. Currently, two types of remotes are integrated, allowing you to trigger various functions remotely. Three exposed pins on the left side are for connecting ribbon style for Sensing Linear Potentiometer, as seen earlier in the video. Next, there are pins for connecting analog potentiometers. The blue connector serves as the analog ground, while the yellow one provides a reference maximum voltage level for the analog to digital converter. The 4 pins of the white connector act as input for this ADC converter, making it easy to connect potentiometers. Moving upward, we have a programmer connector, which I'll mention in more detail shortly. Next, there are 4 pins that allow the connection of external buttons or an encoder for future use. The next connector is the power supply input. The green part is the ground and the red part is the power supply, which is standard plus 5 volts. Then there are a shield connector mentioned earlier, which provides UART signal for MIDI and in addition provides also power. The board can be programmed in several ways. You can connect simple USB ASP programmer. The connector isn't standard, but you can easily prepare a dedicated cable for it. Another option is to connect programmer compatible with the airport standard, such as this example from the company Atmel. The third option is to use microchip programmer with this small connector here, which adheres to the company standards. This method allows for debugging the program loaded onto the microcontroller. On the underside of the board, there are a few soldered bridges that allow you to change the hardware configuration. Earlier, I mentioned that the board can be configured in a completely different way. Here, for example, is a 3D printed case design that allows for mounting the potentiometers to control a synthesizer. Shout out for my colleague Marcin, who created design of that case. The buttons now serve to switch between the controller's profiles, changing the set of parameters being sent. Holding button 1 for a longer time saves the current configuration to memory, so the device starts in this configuration upon powering up. Button 2 allows you to switch between the standard resolution 7-bit MIDI mode and the high resolution 14-bit mode, which provides more precise control over the synthesizer. However, keep in mind that not all musical instruments support this resolution, which may lead to some unexpected effects. Let's see how our device performs with the simple synthesizer on a tablet. This time we'll connect our controller using the USB connector. We can see in the settings that our device has been detected. Let's try generating some sounds while modifying them using potentiometers. Okay, I hope you enjoyed this presentation as well as the device itself. On the website listed below, you'll find the software source code, the KiCad board design, and the documentation. See you next time, and take care!